So our goal for today, and if you haven't written it down, please do so right now. We're going to use inequalities in a triangle, talking about angles and talking about sides. So in this given warm-up problem, the Neighborhood Improvement Project, you volunteered to help build a new sandbox at the town playground. You have two boards that will make up two sides of a triangular, which is unusual, I understand, but let's just go with it. Sandbox. One is 5 foot, so here you have 5 foot, and here's 8 foot. And here are the types of boards that you can have: 15, 12, 8, 5, and 2. Which boards can you use for the third side? Now, one of the assumptions is we are not going to do this. Make a triangle that looks like this. Yes, that is a triangle, but when we say a triangle, we mean there's nothing extra hanging out on the end, okay? So we're saying end point to end point to end point for every single board. So we're also not making any cuts either. So we're just going to keep it simple. So you have an 8-foot board and a 5-foot board. So if this is your 8-foot board, notice that your 5-foot board can go like something like this, like so. Now, what are my options? Now, notice the 5-foot board does not have to be angled that tightly. It could be angled more out. It could be obtuse, like that. Or it could be rightified. There's a word for you. Welcome to neolism. There, it could be rightified, like that. Question, comment? If we try the 2-foot board, here's what happens. 2 feet go like this, and it doesn't touch. And you say, but what if? What if I were to take this 5 and squash it even lower? Well, guess what? It won't even happen. Watch. Here's 5 right there. And if I were to attach the 2 foot to it, how long is that whole thing? It's only 7, which means it won't ever touch to this end. No matter how far you stretch 2 and 5, it won't stretch out. So that means 2 and 5, how does it compare to the 8? It's too small. So we're going to find out later in something called the triangle inequality theorem that the sum of two sides have to be greater than the third side. Now, but let's see over here. Which one else doesn't work? Look, 15 doesn't work. Why, Gehenna, not? Because if I lay the 15 down, and then I tried to put the 8 and 5, here's the 8, and then I put the 5, what happens? They won't ever touch. Because there's the 5, there's the 8, that adds up to 13, which won't stretch out to that point, no matter how flat you make it. And if you make it flat, it's no longer a triangle. It's now segments. So we see that those two don't work. And in the end, it looks as though these ones will all work. So we have extremes, too small or too large, that won't work. So there's a sweet spot, a nice place in between. All right, so now let's take a gander here. And what's nice about today's topics is that it's really common sense when you look at things. So let's take a gander here. Real quick with your partner. Of the 3 sides, which is the shortest side, which is the longest side, and which is the middlest side? AC clearly is the smallest, and if we had to guess, we'd say probably this one is the next one. So let's put that one down and say BC. And then the longest would be AB. Now let's see, how does that compare to angles? So look at this. This is the shortest side. What can you say about this angle right here?
It's the smallest angle.
It's the smallest angle. Wow. In a triangle. Such a tease. All right. So in a triangle, the shortest side is opposite the smallest side. It's also true for the largest side and the middle side. Now, it's also going to be true if there aren't small, medium, and large. If it's isosceles, you have to make an adjustment for that. So this is just a summary of it. I didn't want to get crazy on the full theorems, but let's take a gander here and use it on letter A here. If we were to order the angles by size, that's just a straightforward. Z is clearly the smallest. Okay? Next we have 40, which is the measure of angle X. And lastly, the measure of angle Y is the largest. So putting the sides in order is just a matter of going opposite. So XY is the smallest. Now the opposite of 40 is YZ. And lastly, the leftover is XZ. So that would be placing the side lengths in order from least to greatest. Got to pay attention. Sometimes it'll say from order smallest to largest, largest to smallest. Just pay attention. If it doesn't say which way, then just make sure whatever you say is true. Okay? Make sure whatever you say is true. In this case, small less than this is less than this. All right, now it's your turn. Do B. Okay, I do want to show you something really cool over here. Have you guys ever heard of something called Cornell Notes? Okay. Okay, and it came from Cornell University. All right, so I do want to point out it is a strategy of note-taking called Cornell Notes. And there are essentially 3 sections of Cornell Notes. There is the place where all the information is. Your theorems, your whatever, and this works for any subject, right? Your history lesson, whatever's happening over here, the meat and potatoes. But over on the side, in a small little column that's barely the thickness of your margin, right? It's just some places that help you study. So some questions you might ask yourself, you might write a vocabulary in there. So stuff is just over on the side right here that helps you study. In other words, when you cover up this section over here, or you fold your piece of paper physically in half or physically to the side, this right here is a way for you to study. Oh, so how do I find the shortest side of a triangle? Oh, it's opposite the smallest angle. How do I find the middlest side? How do I find the smallest angle? Oh, it's opposite the shortest side. So these are questions over here that you can ask yourself, and then when you unfold your paper, the answers are over there. So sometimes my notes are set up in that way just to give you an idea of how you can use it. So you can build in study just by folding the paper, okay? So I just wanted to point out the structure of these notes right now. Okay, what do you know about measure of angle 1? So we had an exterior angles theorem. I'll give you a hint. It's somehow related to this right here. So please go ahead and chat with your neighbor. What do you know about the measure of angle 1? We know by the exterior angles theorem that this outside angle is the sum of these two angles. How does this one angle compare to this or this? Always. What we find out is that the measure of angle 1 is always going to be larger than either of those two. Now when we add these two, it's always equal to. But when we just compare it to one of them, it's just going to be greater than either one. So what do we find out here when we tried to draw? How about the first one? Can we draw that one? No. So if this guy here were 5, like so, and then we had the 2 here and the 2 here, they would not touch. Even if I were to flat it, so that's a 2 there, and that's a 2 there, I would still end up with a gap there of 1 inch. And not a triangle at all. How about this one over here? We have the 5 there. And what about the 2 and the 3? Does that work? So here, the 2 would be flat lined there, the 3 would be flat lined there, and of course, not a triangle at all. So what we're trying to do is make an observation about these two compared to the other one. So we see so far that these two add up to be greater than the third side. And let's see here. Do these two add up to be greater than the third side? They do. What about 5 plus 11? Are those greater than 9? Yes. And then finally, 9 plus 11 is greater than 5. So it works for all 3 combinations of pairs. So if I had to draw a not to scale, it'd be something like this. Clean that up. At this one, giving the lengths of a triangle formed. So all you have to do is add these two together and see how it compares to 24. And we see that since they are equal, the sum is equal, the answer is no. Because 10 plus 14 is not greater than 24. So they have to be greater. All right, so now what we can do is use this to figure out some options. So if a triangle already has a length 10, and you were going to attach another side to it that is 14. Notice a couple different options you can do. I can just stick the 14 straight up like this. I can stick the 14 out like this. I can stick the 14 to be obtuse like this. Any of those. However, there are limitations. So what are my limitations? If I were to open this up almost as large as it can get, now clearly I'm going to make it so it looks like a triangle. But if it were, well, let me actually make it look not like a triangle. If it weren't a triangle, what would be the largest it would get? 24. Right. So that would be the largest it would get if it were that way. Now, what if I were to close this up so that the 14 was actually going this way? So it was flat that way. What would be the size of this right here? Possible. The smallest size.
4.
Good. So how did I get those numbers? How did I get those numbers from the 10 and the 4? So, again, we add the two side lengths to get the max, but not including that, so no equal to. We subtract the two sides to get the minimum, not including that one. So a student draws a triangle with a perimeter 12 inches. The student says that the longest side measure is 7 inches. How do you know that the student is incorrect?